moment of inertia, and then start our. And you have to fill these informations. This is section 104, and today's date is 25, right? 25 11 21. Let us come to this. The moment of inertia. What is moment of inertia? How can you represent this? What a symbol? The I is a symbol. Some book, I think your theory book, they're using J. The I is the common symbol used to represent the moment of inertia, and for your book, they're using letter J. What is I? The moment of inertia or rotational inertia. This is equivalent to the mass in the linear motion. Let us say, if you take an object, there are many masses, one, two, three. There are different masses at different locations. When this undergoes the translatory motion, and V1 is equal to V2 is equal to V3, right? And the masses, not much difference, right? They don't have a different effect. Suppose the object is undergoing rotational motion. The object 1, let us take object 2, is rotating at about this, and V1 is lesser than V2. It's clear. What about this R1? R1 is the radius, distance of the object from the center of axis of rotation. This is R2. R2 is greater than R1. Here, the effect of the mass is not the same, right? Effect of the mass is not the same, because the mass which is closer to the axis of rotation has the lower effect. The mass which is far away from the center of axis of or point of rotation, it has the heavier mass. And this put in together, can I say it is mr square? In the linear motion, this does not exist because all the mass have the same effect. So here, the effect of the mass depends on the position of the object from the center of rotation or point of rotation. Suppose m1 is equal to m2. The masses are the same, but their effects are not same. Why? Because they are located at different distance from the point of rotation. So taking into account, we are introducing a new physical quantity called moment of inertia. It is also called as rotational inertia. The simple form of moment of inertia is I equal to mr square. M is the mass. Yeah, even m is the same. If r is different, the effect is different. And this moment of inertia we are going to do in today's experiment. Let me come to this. How we are going to calculate the moment of inertia? It has the formula is a complicated one. And the moment of inertia depends on the shape of the object, the size of the object, the axis of rotation. There are many other factors determine the moment of inertia. Today, we are going to calculate the moment of inertia of the object by a different method. What's the different method? Now you have a spring. You can compress the spring or stretch the spring by applying a force. That energy is stored in the spring as the spring potential energy that will be released wherever required. And the object is attached to a rod. The rod is set into oscillation by using the force from the spring. Now, the object, what kind of motion it is undergoing is rotational motion. Something is related to the moment of inertia. The time period, what is time period? Time taken to complete just one full motion is called as a time period. The time period of the system is given by this formula, T equal to 2 pi square root of I over D. What is I? I is the moment of inertia of the setup. D is a constant, like a spring constant. The constant of the given spring is 0.0255. From this, can I get your I? Square root of I over D is equal to T over 2 pi. from this, if I want to remove the square, I have to, sorry, square root, I have to take the square. I is equal to d t over 2 pi square. This is the formula I'm going to use to calculate the moment of inertia of the object. And here d is a constant, 2 pi is a constant. Only one variable in this equation, in this formula is substitute the t of a particular configuration of the material of the system. Then you will get the moment of inertia of the particular configuration. Right? Just substitute t, you will get the moment of inertia. This is the method we are going to use to calculate the moment of inertia of the system. I told you there are three parts in this. The first part is moment of inertia I of the rod. The moment of inertia I of the rod. How to calculate this? By using the same formula, only rod. Now I rod is equal to d t rod. That is the time period we are calculating only for the rod. By using this formula, I can calculate the moment of inertia of the rod. Let us see how we are going to collect the data for this part. I told you there are three parts in this. The part number one, this is the data. Now let us come to this, the brush drawing thickness. Okay. Now this is the data I'm going to collect. The number 1, 2, 3, the T10. What is T10? T10 is the time taken for 10 oscillation. What is the difference between this column? Okay, this column and the other column. Okay, what is the difference between this column and this column? Small t, capital T. Small t10, that means the time required to complete 10 number of oscillations. The total time required to complete a particular number of oscillations. What is capital T? The capital T represents the time period, the time taken for only one oscillation. Time taken to complete only one oscillation is called as the time period. How to get it? T10. T10 is the time taken for 10 oscillation. You are getting some time, some value. Divide this by number of oscillation. What is the number of oscillation here? 10. Then you will get the time period. Substitute the time period in the formula. What is that? I rod is equal to d t by 2 pi whole square. Substitute this t value in this formula, you will get this answer. Repeat this experiment for 3 trials. Trial 1, trial 2, trial 3. Just you are taking only rod, you are finding the time period, and then you take the average. Now you have 3 values of moment of inertia. Take the average of all the 3 values. This is part number 1. Come to the part number 2. Here we are going to calculate the moment of inertia of the point-like masses. At the end, we are going to measure, to calculate the value of point-like masses. Now here R. What is R? R is the radius of rotation. The radius of rotation, we are fixing it as 5 centimeter, 10 centimeter, 15 centimeter. Centimeter I'm writing in terms of meter because SI unit of distance is meter. Can you do this? Square and write it. T10. T10 is the time taken for 10 oscillation. First to fix the 5 centimeter radius and measure the time taken for 10 oscillation. Write T10. Divide this by 10. You'll get this. The rod and masses. How to calculate this? Using the same formula because this T belongs to rod and mass. Substitute this T in the same formula, you will get this. Repeat this experiment for different values of R. Next R is 10 centimeter, 15 centimeter, 20 centimeter, 25 and 30. And find its time taken for 10 oscillation T10 and find its corresponding capital T, that is time period. Substitute the time period in the given formula, you will get the I masses, I rod plus masses. How to get this I masses only? Look at here. the I rod plus mass is equal to I rod plus I mass. From this, I mass, I rod plus mass, I rod plus mass minus I rod. What is I rod? I rod, this average value is I rod. And this is I rod plus masses. Take this value, subtract, bring this value and substitute here. The difference you will get I masses. Repeat this experiment for every column. After completing this part, we are going to draw the graph. The graph between the I masses versus R square. I masses should go to Y axis and R square should go to X axis. And calculate the slope. From the slope, we are going to calculate the value of M, the value of point-like masses. This is part number 3. And in this part, we are going to measure or estimate the moment of inertia of the different shapes of object. Previously, last part, we found the moment of inertia point-like masses, small masses.
Doctor, in the
Yes.
previous in the graph point here, what do we have to to calculate or what, doctor?
See, do you see this one?
The mass
Shiva?
of what?
What
Yes,
is
yes.
that? Yeah. The mass we are going to calculate.
Okay.
And in the part 3, we are going to place the sphere in the setup and find the time taken for 10 oscillation for the sphere. Divide this by 10. You'll get substitute in the same formula. What is the formula? D T over 2 pi square. If you substitute this T here, the value of moment of inertia, you'll get this. Then repeat this experiment for hollow cylinder, solid cylinder, and disc and find the T10s and find corresponding T. If you substitute this T here, you will get this answer. Same formula. If you substitute the particular value of T, you will get the moment of inertia of the particular configuration. Right? And there is no graph for this, only graph for second schedule of this experiment. And then after this, we are going to write the source of error and conclusions. First, let me share you the video. The video will explain you different part of the experiment and how to handle each part and get how to get the data in this experiment. At the end of the video, I will share the data. You can copy the data to your paper, and after copying the data, I will explain you how to draw the graph. Right? Any questions, Shubha?
Doctor, after the video, can you explain us how to calculate the values?
After video.
Yes, yes.
Inertia. This is also called as the rotational inertia. Let us come to this is related to the rotational motion of an object. Let us come to the objective of today's experiment. Today we have two objectives to determine the moment of inertia of the pair of point-like masses through a range of distances from their turning points, and then to determine and compare the moment of inertia of series of continuous objects. Now these are the two objectives of our experiment today. And this is our experimental setup, and this is the spring. And here we are going to compress the spring. I think the spring potential energy already we discussed some time back. And we are going to compress the spring. We are doing some amount of work in compressing the spring. That energy is stored in the spring as a spring potential energy, and this provides energy for oscillating the objects. If the masses, point masses m1 and m2, the two masses are separated by some distance. This is the radius of rotation. This radius This radius should be the same. And I'm going to set into oscillating this object, and find the time taken for one oscillation, the time period. The time period of the oscillation is given by this. The t is the time period, is equal to pi I over t. I is the moment of inertia. 2 pi is is a constant. Square root of I over t. I is a constant. Sorry, the moment of inertia. The t is a constant. By using this formula, I'm going to calculate your I. Now, let us see. The t is equal to 2 pi I over square root. By rearranging this, square root of I over d is equal to t over 2 pi. If I want to remove the square root, I over d is equal to t by 2 pi square. I is equal to d into t by 2 pi square. This is the formula I'm going to use to calculate the moment of inertia. D is a spring constant. The constant of the spring is given here. And this is the constant of the spring, 0.0255 Newton meter per rad. And I'm going to substitute this value here. And t is the time period. This I'm going to measure in our experiment. The time period divided by 2 pi. 2 pi is a constant, you know it. I'm going to calculate the moment of inertia of the object by using this formula. This. And we have three parts in this experiment, right? The d constant value of d. We are going to substitute this. And the second part, the first part I mean, the first part is calculating the moment of inertia of the rod only. The moment of inertia of the rod only. The T10. T10 is the time taken for 10 oscillation, because we cannot calculate, we cannot measure the time period directly, because the time period is a very short duration. When the duration is short, if you measure the short duration manually, the more amount of error will be introduced in that. In order to reduce the magnitude of error, we are measuring the long duration, and divided by the number of oscillations, you can get the time period. And if you substitute this t value in the equation already we derived, here, this is the t corresponds to the rod only. If you substitute this t here, you will get I rod. This is the moment of inertia of the rod only. The next, we are going to calculate the moment of inertia I for the two identical masses as a function of the distance r at which with a mass m is rotating about the fixed axis. And this is a schedule we are going to follow. The data, this is r. R is the radius of rotation. We are taking 0.05 meter, 0.1 meter, 0.15, 0.2, 0.25 meter. This is square, r square. We are squaring this is in meter square. T10. T10 is the time taken for 10 oscillations. We are measuring the time required for producing 10 oscillations. This divided by 10, you will get the time period. The T capital T is the time. This time period corresponds to the rod and masses. The rod and masses. If you substitute this T in this formula, you are going to get the moment of inertia for rod and mass. Substitute that here. The rod and masses. How I'm going to calculate the moment of inertia of the mass only. Now let us see here. I rod plus mass. That means moment of inertia rod and mass. I can write it as moment of inertia rod separately, the moment of inertia mass separately. I want only moment of inertia of the mass. The mass is equal to I rod plus mass. It's together minus I rod. The I rod, we are getting this in the schedule number 1. And if you subtract this from this, you will get I masses. We are going to use this here. This column will give the moment of inertia of the I rod and mass. Here, the average value of I rod you're going to get. If you subtract this quantity from this quantity, you're going to get I masses only. And repeat this experiment for different values of R. Initially 0.05 meter R, then 0.1 meter, 0.15, 0.2, 0.25, and complete this schedule. Now, I'm going to introduce the different part of the equipment we are going to handle here, and this is the spring. I'm going to give do the work on compressing the spring. Now, when energy is stored in this, and the energy is released in terms of the, this is my rod working, and the total length of the rod is about 60 centimeters. See, this is 60 centimeters. I'm going to fix the exactly the middle point. The middle point, this should be 30 centimeters. From this edge to the middle of this is 30 centimeters, and fix this. And fix it here. I'm going to cross verify it. Take the ruler, and you know this is 30 centimeters, and fix it here. And cross verifying 30 centimeters. Check the other edge. Is also equal to 30. Now it is exactly at the middle. Now after fixing this, I'm going to measure the time taken for 10 oscillations. Now this is the mean position, and you should not rotate too much, more than 90 degrees. You should not rotate like this. This is a normal position. You can go up to maximum 45 degrees. Theoretically speaking, you should not go more than 30 degrees. Since the instrument is old, I can go bit higher to sustain the oscillation. 10 oscillations. Now bring up to this 45 degrees, leave. Now it is oscillating. How to find one full oscillation? If it starts from here, it goes this end and come back. This is called as one full oscillation. We have to count the time taken for 10 oscillations by using the stopwatch. This is the stopwatch I'm going to use today.
Doctor, just 45 degrees
I'm going to switch
from
on
the
the
center.
stopwatch. Yes, Shiva?
Just 45 degrees,
Yes, yes.
not 90.
Theoretically speaking, you should go less than 30, but it is the old, the instrument is old. Therefore, we are going up to 45 degrees.
45 degrees.
Yes.
But Doctor, how I can measure the angle?
Approximately.
Approximately. Okay.
Yes. Now, see this. I am giving the oscillations. Now I'm going to start. See, I'm going to start this as a reference. Now I'm going to start. Now, yes, I pressed. Now this is running. Number 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, this is the time taken for 10 oscillations. I can write this is the time taken for 10 oscillation, 27.31. And repeat this experiment for 3 times. Same experiment for 3 times, write the 3 times. And T equal to 2.731. This is divided by 10. Number of oscillations is 10. You divide this by 10, you will get T. Substituting this T in the formula, other formula. Already we discussed about that formula. Yes. If you substitute the T value 2.731 here, I will get the moment of inertia for the rod only. And repeat this calculation for the 3 values and get the average of this. And this average give you the average I rod. Average I rod. Then coming to the next part, I'm going to, these are 2 point masses. I'm going to find the mass of each piece and attach this at the either end. Now what is the radius here? Radius is 5 centimeters. That means from this screw to this screw should be 5 centimeters. See, this screw to this. This screw to this screw, 5 centimeter. See, center of this screw, 5 centimeter. And similarly here, 5 centimeter. Now see this. It starts at 5, ends at 10. This is 5, this gap 5, this gap 5. Now radius is 5 centimeter. Then I can start the oscillation. Now give the oscillations. I'm going to start now. Yes, start. 1, 2, 3, 4, 5, 6, 7, 8, 9. Stop now. 10. Now this is the time taken for 10 oscillations. T10 is 30.68. Now T is divided by 10, 3.068. If you substitute this T value in this formula, you will get the I for rod and masses. This time, this corresponds to rod and mass. If you substitute this time here, you will get this. And repeat this experiment for various values of R. 0.1, that is 10 centimeter. Then increase this value. See, this is 10 centimeter. And change this also 10 centimeter. This 10, this 10. Again, find the time taken for 10 oscillations. Next is 15 centimeter. Then increase this 50. This is 15. And continue. 20. This 20. Another 20. 25. And this distance should be 25. You can adjust, change the values of R and measure, measure the time taken for 10 oscillations and time 5. And you will substitute this T in the formula. You will get I rod and masses. Subtract this value from this value, you'll get I masses only. Now you will get all these things, right? And if you do the squaring, 0.05 into 0.05, what do you get here? You can write it as 2.5 into 10 to the power of minus 3. Continue this, and the last one, 0.25 into 0.25, how much you are getting? See, this is a different one. Press ENG. See, 62.5 into 10 to the power of minus 3. 10 to the power of minus 3 you can keep as a common. 10 to the power of minus 3 you can keep as a common, right? And similarly, keep as a common, you can draw the graph only for the number. Similarly, here I will get 10 to the power minus 6. I will explain you great detail in the regular class. Now, this will keep this as the power, and you can draw the graph only for the numbers. After completing this, I am going to draw the graph between I masses versus I square. I masses should go to y-axis, R square should go to x-axis. Now, let me take this. I masses, some value, right, into 10 to the power of minus 6 kilogram meter square is the unit. You're going to take the number here. And here, R square. If you see the R square, the power, you can keep the 10 to the power as the unit. 10 to the power of minus 3 meter square you can keep as the unit. You can write the values and draw the graph. Try to draw the graph as big as possible, and the bigger graph will give you minimal error. The error should be as low as possible. You want to get a minimum error. Now, there are many points. The majority of the point should be lying on the line. If 1 or 2 points not lying on the line, let us not worry about that. Now, this is a point. We are going to
Doctor,
select 2 points
you didn't
to
measure
calculate
the delta x
the
and delta y.
slope. Yes?
You didn't measure the delta x and delta y.
Later.
Mm-hmm.
And write this. This is x1, and this one is your y. And this is your x2, and this is your here you have to write delta x is equal to something, delta y equal to something. I will explain this delta x, delta y in the regular class because I don't have the example values, right? Now I'm going to calculate the slope now. The slope is equal to y2 minus y1 by x2 minus x1. y1, y2, x1, x2 you can get from the graph. Now coming to the unit. Now see the unit. 10 to the power of minus 6 kilogram meter square, 10 to the power of minus 3 meter square. Now meter square get cancelled. Here 10 to the power of minus 6 kilogram and 10 to the power of minus 3. If you go to the numerator, what if you have some number into 10 to the power of minus 6, 10 to the power of 3. Minus 3 if you go to the numerator, it became plus 3. Now the value into 10 to the power of minus 3 kilogram. Multiply the value with the 10 to the power of minus 3, then you will get the slope in SI unit. Now, I am going to calculate the masses. How to calculate the masses? The moment of inertia of the masses, I mass, is equal to m r square. M is the mass, r this. Since we are using the 2 masses, the I masses is equal 2 times this m r square. My aim is to calculate m. M is equal to 1 by 2 I mass divided by r square. Since we are adding 1 mass left side, 1 mass right side, therefore I am adding 2. There are 2 masses. M equal to of I masses by r square. And come to the graph, the meaning of the graph, meaning of the slope. The meaning of the slope is y quantity by x quantity. What is y quantity? I mass by r square. I mass by r square is the meaning of the slope. Wherever I have I mass by r square, I can replace with the slope. Now come to this. I mass by r square, I can replace with the slope. That means slope divided by 2. Whatever the value you are getting as the slope, you divide the slope by 2, you will get the m in kilogram. This is the first part of the experiment. The next part, the third part in this experiment is measurement of moment of inertia I for continuous object. In the part B, we measure the moment of inertia point-like object. It's a small piece of object. We measure the moment of inertia of this. Now, I'm going to measure the moment of inertia of different shapes. Continuous object, sphere, hollow cylinder, solid cylinder, and disk. Place the cylinder, the sphere, and measure the time taken for 10 oscillations. Set the oscillation, measure with the time taken for 10 oscillations. Divide this by 10, you will get t. Substitute this t. This t corresponds to the sphere. If you substitute this t in the formula, you will get the moment of inertia of the sphere. And repeat this experiment for various shapes of the object. First, I'm going to take the sphere. This is the sphere. And detach this by using the screw. And you can do this. Take this and place it here. If If I rotate this is rotating, it's not oscillating, right? If I want to make it oscillation, keep this and give the type to the screw. If I type this will undergo oscillation. If you are not typing, suppose if I lose it, it's not undergoing oscillations. Now give this type to this. Now this will undergo oscillation. Now I'm going to measure the time taken for 10 oscillations. Time taken for 10 oscillations. Now I'm going to start 0. Now I'm going to start now. Yes, start. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to stop now. 10. The time taken for 10 oscillation is 16.990. 16.90 is the time taken for 10 oscillation, and time taken for 1 oscillation, this divided by 10, 1.69. If you substitute this value in the formula, you will get the moment of inertia for the sphere. Next, hollow cylinder. I'm going to take the hollow cylinder. There are 2 cylinders we have. Which is hollow cylinder? This is hollow. See, inside is nothing. It is hollow. And this is solid cylinder. There is no hollow. The material is filled completely. The next is hollow cylinder. And remove this and keep it safely. And the next, take the hollow cylinder. There is a mark. Keep the mark facing you. And give the height. Give the oscillation. And you can find the time taken for 10 oscillations. Record it here. And divide by 10, you will get the time period. Substitute the t value in the formula, you will get this. The next is solid cylinder. Following this, take the solid cylinder and place it here and give the time to this and give the oscillation. Find the time taken for 10 oscillations. Record it here and divide it by 10, you will get t and then the moment of inertia. The next one is disk. This is the disk. This is the reference point. Keep it here and give the time to this. Rotate this. Now this is set into oscillation. I can measure the time taken for 10 oscillations. Record it here. Divided by 10. You'll get the time period. And substitute this t in the formula. You will get the moment of inertia for the disk. And come to the conclusion. The sources of error. What are the major and minor sources of error? I will explain you detail in the regular class. And coming to the conclusion, the average mass of the point-like masses was found to be, what is the mass you got? You can write it here. And then you are comparing this. I will talk more about this in the specific lab things. Today we are. Do you have any doubt? Shubha?
Doctor,
Yes.
the mass m equal to slope over 2.
Yes.
Do I have, doctor, to write the equation or no? Directly the m equal to slope over 2.
M equal to slope over 2.
Directly. I can
Yes.
write it m equal to slope over
Yes.
2.
Now you can copy the data given here and copy only this data. The others I will tell you how to calculate. After copying, please tell me. Copy this data on your paper.
Doctor, can you remove the box here? Can't see the number 2.
Number 2.
Okay. Now it's good.
Doctor,
Yes.
what is capital T?
Capital T is the time period.
So what is the difference between small t and capital T?
Small t is the total time. Capital T is the time period for one oscillation.
Doctor, what's the meaning of the isolation?
Not isolation,
No,
oscillation.
yes,
Oscillation
the
means it is
oscillation.
oscillating. It starts from point, go to the other extreme. Suppose you are starting from your home, right?
Yes,
You come to the college and go back to your home.
yes,
This is one oscillation.
one isolation. Hmm.
Yes.
Doctor,
Yes.
in T capital, I divide T small over 10.
Yes. 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 This page done, Shiva.
Yes.
You copy this data. You have to copy only this. After completing, tell me, Shiva. Done?
Yes, doctor, please wait.
Okay. You copy this data also. You copy only this.
Doctor, can you remove the box?
Doctor,
Yes.
I for road and masses, where can I find them?
Copy this, I will tell you.
Okay. Done.
Okay. Come to the first schedule. This is only for the rod. Now this is T10. This is T. The capital T is the time taken for only one oscillation. Divide this over 10. Divide this by 10, you will get this. And this divided by 10, you will get this. This is 2.245. Substitute this value in the formula. For example, if you take yeah, the formula, I'll show you. I will show you the formula later also. Substitute this t value. Where is that? This t value in the formula, that is d t over 2 pi whole square, and you will get this. and substitute this t value in the same formula, you will get a different value because t is different. The final answer will be different. After calculating three values, find the average of that. Write the average here. Is average moment of inertia for the rod only.
Doctor,
Yes.
can you complete I rod? I don't understand.
You know how to calculate this?
No, no, doctor.
Substitute the t value here. I is equal to 0.0255 into, what is that t value there? 2.472. 2.472 divided by 2 pi square is equal to 3. What is that? 3.95. 3.95 into 10 to the power minus 3.
Doctor,
Substitute this t value for the second column, second row, you'll get this one. Yes.
0.0255 is a constant.
Yes. The constant is printed on your first page. Now that part is over, right? Let us go to the second part. Complete the three and get the average.
Doctor,
Yes.
can you back to the white paper? I want write, please.
You can write later.
Okay, doctor.
Doctor, the average, sum all the values and
Yeah,
divide by
you
3.
don't know how to take the average.
The sum of the three values divided by 3.
Yes.
Am I right?
Yes. And coming to this, and we have to square this. 0.05 square. You will get this, 10 to the power of 3. And square each value, 0.01 square and 0.15 square, write this. It is better to write in terms of 10 to the power of minus 3. See, 10 to the power of minus 3 is common for all the values. For 10 to the power of minus 3, I can take it as a unit and draw the graph only for the number 2.5 to 90. It is easy for me to draw the graph for this, right? And then t, this is t10. Divide by this 10, you will get t, capital T, 2.793. Substitute this t in the same formula, 0.0255 into 2.792 divided by 2 pi whole square. You will get this answer, right? 5.04 into 10 to the power of 3. And you can repeat this for all the rows. The final one is 81.63. This is a time t10. T is 8.16. Substitute this t 8.16 in the formula. I will get the moment of inertia is 43.05 10 to the power of minus 3. And these are the rod plus masses. This is the time I found for the combination of rod and mass. And this gives you the moment of inertia of the rod and mass. Now I want to find the I masses only. How to get it? The I masses is equal to I rod plus mass minus I mass. That means this value, see, take 5.04 into 10 to the power of minus 3. Suppose if you take this average value, what is the average value you are getting here, right? Whatever the average value you are getting, just write that value here. Now the difference is this, 1.09 in 10 to the power of minus 3. Clear? And repeat these steps for all the rows in the schedule. And coming to the final one is 43.05 10 to the power of minus 3. I rod is 3.95 10 to the power of minus 3. And this is your answer for the last one. I'm going to draw the graph between I masses versus R square. I masses versus R square. Let us see the graph. First, I'm going to find delta x. If we go to the schedule, delta x, you should take R square, right? R square is delta x. The maximum is 90 minus 2.5. 90 minus 2.5. I told I'm going to keep the 10 to the power of minus 3 as a unit. Now I'm not going to use that. If you count the number of units in the x-axis, you may get the maximum. 90 minus 2.5 divided by 18. How much you are getting? 4.86. Can I take it as a 5.0, Shiva? Shiva?
Yes, doctor, we can.
Yes. Into 10 to the power of minus 3 meter square. I told I'm going to keep this as the unit, right? Delta y. If you come to the y-axis, what is delta y maximum value? 39.1, 1.09. 39.1 minus 1.09. Whole divided by, if you count the number of units in the y-axis, you may get 25. 39 minus 1.09, how much you got? 37 point, no, divided by 25. The final answer is 1.5164. Can I take this as 2.0? Shiva?
Yes,
Anyone online?
Yes,
yes,
doctor.
doctor, we can take.
2. Next, I'm going to draw the graph. Don't forget to write the quantities and units properly. In the x-axis, I'm going to take r square is the physical quantity into 10 to the power minus 3 meter square is the unit. I told 10 to the power of minus 3, I'm going to take as the unit. Here, I mass into 10 to the power minus 3 kilogram meter square is the unit. Now I'm going to write the values. How to write the values? See, x-axis, what is the minimum? 2.5. The increment is 5. Yes.
The unit for the delta y is what?
See this, what I've written here. Kilogram meter square. See the schedule. It is printed clearly.
Okay.
This is 5, 10, 15, 20, 25, 30, and so on. It's clear. And come to the y-axis. Y-axis, what is the increment? Is 2. The starting value 1. Therefore, here also I can take starts from 0. This is 0, 2, 4, 6, 8, 10, and so on. If you follow this increment, don't draw the smaller graph. I think most of you are drawing smaller graph. If you draw the bigger graph, the error introduced will be minimum. We want the minimal error. Yeah, I forgot to write something here. What is that? Delta x is equal to 5 into 10 to the power minus 3 meter square. Delta y is equal to 2 into 10 to the power, 2 into 10 to the power of minus 3 kilogram meter square. Now you can plot the point and connect the majority of the point, the line should connect the majority of the points. Now I'm going to calculate the slope. This is your x1, this is your y1, and this is your x2, this is your y2. Come to the calculation, the slope calculation. y2 minus y1 divided by x2 minus x1. 10 to the power minus 3 kilogram meter square is the unit in the y-axis. 10 to the power minus 3 meter square is unit in the x-axis. Now meter square get cancelled. 10 to the power of minus 3, 10 to the power of minus 3 get cancelled. Whatever you get the number, that is in kilogram, right? Your slope is. Then how to calculate your m? This is the formula. I masses. A simple formula is m r square. How many point-like masses we have? 2. One on the left side, one on the right side. Therefore, I am adding 2. I want to find m. M is equal to 1 over 2 I mass over r square. Now come to the slope. What is the meaning of the slope? The slope is equal to y quantity. What is y quantity? I mass by r square. Wherever I have high mass by r square, I can be replaced with the slope. Look at here. This is equivalent to slope. Therefore,
So, Doctor,
your m is equal to slope divided by 2 something kilogram. Is it clear, Shubha?
yes.
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 So we'll use the final formula.
Yes.
Okay.
The next, there is one more part is left in this. Where is that? There is one more part. The second part is over. This is the third part. I told you we had to do the calculation. You know, this is this data you have. This data you have. Now you want to find the t. How to find? This T10, time taken for 10 oscillation. Divide this by 10, 1.42. Divide this by 10, 1.065. Now you found the T, the time period for different shapes of the object. Substitute the time period in the same formula. Substitute the time period of sphere on the formula, that is T 0.0255 into 1.42 divided by 2 pi whole square. If you complete that, you are getting this answer. Substitute this t value. This t is smaller than the previous one. Substitute the t value in the same formula. You will get the moment of inertia for hollow cylinder.
Doctor, again, in which
It's still
formula?
smaller. And substitute this value in the same formula. You will get the corresponding moment of inertia. Is it clear, Shiva?
Yes, but again, Doctor, which formula?
Only one formula we have for this equation. Sorry, this experiment. Only one formula we have for I. What is that? D T over 2 pi square. This is the formula. And this is constant, 0.0255. And substitute the value of t, 2 into pi square. If you substitute the value of the t, you will get the corresponding moment of inertia. If you substitute the t for sphere, you will get the moment of inertia of sphere. If you substitute the value of t for cylinder, you will get the moment of inertia of the cylinder. Clear? Yes. Yes. That is the method of calculating the average.
Yes, doctor, but we have to write the 10 to the power minus 3 or just the values 3.95
10
plus
to the
3.
power of minus 3 also important.
No, I mean in the average when I calculate it.
Everything. Add all the number divided by number 3.
Okay.
Now this gives you the source of error. Source of error, the major source of error introduced in the calculation of point mass of point like object and the amount of inertia of the continuous object, or in the measurement of time period t we are measuring manually, and the radius of rotation also we are measuring it manually. Both could be the major source of error for this experiment. The minor source of error introduced in the calculation of mass of point like object and the moment of inertia of the continuous object, or in the is in the is in the value of the constant provided. That the value of d is given. That may be a different values because it is used since a very long time, and that source could be the minor source. Coming to the conclusion, the mass of the point like object was found to be how much m you got in your experiment. Write the m value here. Right? Write the m value. And the next one, the moment of inertia of the continuous objects, sphere, hollow cylinder, solid cylinder, and disk was found to be. Here you write the moment of inertia for the sphere first, then hollow cylinder, then solid cylinder, and the disk. Write this in the order as indicated in the conclusion. Any doubt, Shiva?
Doctor,
Yes.
sorry, can you tell me the conclusion too? I don't understand. What I write here?
The schedule number 3, right?
Yes, and
Schedule number 3.
yes.
What is the moment of inertia of the sphere? Write the moment of inertia of the sphere here. The next is hollow cylinder. Write the moment of inertia of the hollow cylinder after the comma. After the second comma, write the moment of inertia of the solid cylinder. And after and, you write the moment of inertia of the disk. Write the moment of inertia you reporting in the schedule 3.
Okay, Doctor, clear now.
Okay. Any doubt, Shiva?
No,
Can I
no.
leave, doctor?
Yes, if you don't have any questions, you can. Next week is a holiday. After
Yes.
that, we are going to do the experiment number 10 for your section.
Okay,
Last experiment, doctor.
Yes.
Okay, thank you.
Okay.
Doctor,
Yes.
I tell with you in the first class. I want come to you. I will come now. No problem.
For what?
For theory.
Okay.
Okay, Doctor. Thank you.
Yes. Hmm. Write in the same method. Follow the same method what I used in the schedule. A different one. Yes. Yes, yes, yes.
Also, doctor, the eye masses.
Yes, everything write in 10 to the power of something.
Mhm.
Scientific notation.
Okay.
Doctor,
Yes.
in last experiment number 8, I didn't get the grade for the experiment.
I did not enter for your section. I will enter today.
Okay, thank you, Doctor.
I forgot to enter. I finished marking, but I forgot to enter.
Doctor, the percentage of error, how can I calculate?
Did I talk about the percentage of error calculation? Did I talk about that in this experiment?
I don't know, Doctor, but
Check with your friends. If you are you attending the class regularly, continuously?
no, I attend the class, Doctor, but I
Then